In this video, we'll be covering the concept of transformations. Transformations, number one, allow you to very efficiently and quickly sketch a curve without having to do very much work. Number two, it allows us to be able to look at an equation and simply know more or less what that equation is going to look like on a graph. So you'll notice here in this set of information, we have very clear definitions of what a vertical shift might do. So a plus sign on the outside of a function might shift it up by a certain number of units, in this case c units. If I have a minus sign on the outside of the function, it will shift it down 2 units, or c units in this case. If I'm adding or subtracting into the function, then it's going to do exactly the opposite of what you think it should do. So again, x minus c would tell you that you kind of want to moving to the left because that's where the negative sign or the negative numbers are. However, with an x minus c inside the function, you're actually going to move to the right. Likewise, if I say I have f of x plus c, where the plus c is on the inside of the function, once again, you're thinking you're going to move to the right because that's where the positive signs are, the positive numbers are, but we're actually going to move to the left. You'll also here see that we have a reflection if I put a negative in front of the function over the x-axis. This should make sense based on some of the graphs that you have seen, as well as a reflection in the y-axis where I plug a negative in for x and replace my, again, f function inside with a negative. Then you have vertical stretch and vertical compress. You may also refer to these as a vertical stretch being a elongation. You may look at the vertical compression as though it's being a shrink. Now the difference between these two, you'll notice that they are very, very similar. The difference is that the c value is larger, is a positive number for the stretch, which should make sense. It means that all the y values of the function are being increased by a certain amount. And then the second detail is that if it's between 0 and 1, you should notice that it is a compression. It is taking the value and it is shrinking the value and making it smaller. So let's look at a couple of examples real quick here. If g of x equals to x cubed minus 2, we know what the cubic function looks like. In the last video, we should have identified that the cubic function looks something like this. There is one very important point. That very point important we sometimes refer to as the inflection point. This point is the point that's going to shift in any which way it tells us to. Now the original function is y equals x cubed. So when I subtract 2 from this function outside of the cube, now again, this is different than this. And this is the one we're looking with. Okay, so this one right here tells me we're going to shift down 2 units because the function is the cube. The function is the cube. So that means that this graph will actually look something more like this. 1, 2, that's where my point is now, and I still have more or less the exact same curve. Now, yes, if we wanted to find more information about this curve, we could. But 9 times out of 10, all we really want to do is get a good understanding of what the graph looks like. If we wanted to find x and y intercepts, we could go ahead and do that algebraically. So let's look at the next example. The next example here is h of x is equal to x plus 1 cubed. Now keep in mind, for this curve, h of x equaling to x plus 1 cubed, the plus 1 is on the inside of the curve, or inside of the equation. So it being on the inside tells us that I would think about going left or right. Now I'm going to write both those down, and I'm going to identify the fact that the plus sign tells me to go to the right. So in reality, I really want to go to the left. Again, the plus sign makes me think I want to go to the right, but I really want to go to the left side. Okay, again, that plus sign changes based on our rules. When it's changing the sign on the inside, we do the opposite of what we think it's going to do. So that plus 1, again, one more time, tells me to go to the left. So this curve right here will simply move over 1. That's where my new center of information is what I like to call it. And it looks still like a cubic curve. Okay, so again, these three are all cubic functions, and it's this curve is transitioning to this one. Now, if I happen to have a third function, let's just call it k of x, and let's call it the x plus 1 cubed minus 2, what would happen to this function? Well, let's be very clear about it. It is the transition of a minus 1 on the inside, sorry, a plus 1 on the inside, so we're thinking about going to the right, but we're actually going to go to the left 1 unit. And then this minus 2 on the outside of that cubic tells me to go down 2 units. So I'm still going to have a cubic. The original cubic function should have looked something like this. But now I'm going to take that cubic and I'll move it left 1 unit and I'll move it down 2 units, and that's where my center of information now occurs, still looking more or less the same. Now, I drew it as though it goes through that origin, but I can't be certain that it does. So I want you to be very clear that this, I know, goes through that point, but I don't know any other piece of information about this curve. So that covers the shifting left, right, up, and down. Again, outside the equation is up and down. Inside the equation is left and right. Next, let's take a look at the following curves here. These are both, you'll notice, square root functions. Now, in terms of a square root function, again, every square root function looks more or less about the same. So it looks something like y equals x, or sorry, the square root of x, and it looks to start like this. Now this one right here, you'll notice, has a plus on the outside, a minus 1 on the inside, and it has a negative sitting out front. Now let's recall that negative sitting out front will do a reflection in the vertical change. Now I'm going to be very clear about what I mean by that. The plus 1 on the outside of the equation will shift my function up or down. The plus 1 specifically shifts it up. The negative 1 outside the equation should also do a vertical change. So in this case, I should be able to recognize very quickly that the g of x equaling to a negative square root of x minus 1 plus 1. The plus 1 is a shift of up 1. That minus 1 in here makes me think I'm going to go to the left, but I'm actually going to go to the right. Again, any inside change is going to be a left or right, or more appropriately, a horizontal modification. And this right here is what I like to call a vertical flip. So this equation is going to be shifted right 1, up 1, and it's going to be flipped vertically. So it will look more like this, going right 1, up 1. It would be up here, but since I'm flipping it over the x-axis in the vertical direction, it's going to be somewhere down here. Actually, I'm sorry, that's not right. It's going to be here, but it's going to go ahead and flip from this position. So it's going to flip like this instead. Okay, let me be more clear about that one more time. The way that this particular manipulation happens is it must work from the inside out. So the interior is the right 1. So I'm going to move this over right 1. I'll move it to there. The next thing I have to do is vertical flip. So when I move this over to here, I'm then going to flip it upside down like this. And then I'm going to move it up 1. Again, to do these transformations, it happens from the inside out. So when looking at the next one, this h of x function, equaling to the square root of negative x minus 1 plus 1, we're going to want to treat this one in the same way that we treated the last one. The problem, however, is that this negative sits where it is. I first need to transition this function to this. Again, factoring a negative out of all the pieces in there. So that way I can view this as, what is this change here first? That first change is a left 1. What's this change right here? Well, that change is a horizontal flip. And this right here is a up 1 unit. So again, those are the 3 transformations. If asked, you must explain them clearly, just like these 3 right here. Those are the 3 transformations. If asked, you must explain them clearly. So this right here is going to be simply me trying to determine what I have to plug in to make this work. Well, you'll notice that we're going to go up 1, we're going to go left 1, and we're going to have a horizontal flip. Well, this curve should look something like this to start. But since I'm horizontally flipping it, it's actually going to be flipped facing that direction. And I'm also going to move this left 1 unit. So I'm going to move it 1 over here. I'm going to flip it so it's facing that direction. And then I'm going to move it up 1 unit. So right here is what this curve should look like. So that covers your cubic and your square root functions. Keep in mind that all functions, be they, again, square root, quadratic, cubic, rational, exponential, logarithmic, square root, cube root, and absolute value, regardless of the type of function, this is the rule that we're playing with, and all of these little details still coincide. So on this last curve right here, which is an absolute value function, you will notice that there is a 1/4 sitting outside the absolute value. Well, that 1/4 should make you think that it's going to be a vertical modification. And because it's a 1/4, it's going to do exactly what you think it's going to do. It's going to vertically shrink this graph. So on my graphing paper here, I'm going to go ahead and have y equals 1/4 absolute value of x minus 3. I know that this is going to shift it down 3 units. And I know that this is going to have a vertical shrink by a factor of 1/4. Again, that has to be in there on your explanation because it's not totally inherent that we know exactly what it's going to do. But based on this number, we can again shrink it by a factor of a certain amount. Now, after we've identified that detail, let's go ahead and look at what the curve originally looked like. The curve originally would have looked like something like this. This is y equals the absolute value of x. If I were to go ahead and move it down 3 units, that would look something like this. 1, 2, 3. It's going to look very, very similar. What would this curve look like when it's multiplied by a factor of 1/4? Well, it's going to shrink or compress this graph vertically. So think of, though, this thing is on a spring, and I'm going ahead and pushing these two things down. What's going to happen to all these values? Well, they're going to spread out further. And again, you're going to have a compression by 1/4. So all these values are going to be 1/4 the value that they're supposed to be. But keep in mind, this is an anchor point of this curve. So when I go ahead and stretch it or shrink it by any certain amount, 1, 2, 3, that anchor point remains the same. But when I go ahead and I try compressing it, it's actually going to end up being a little bit wider than the previous example. So if I go ahead and put a dotted line in here, this is what the original curve would have looked like. This is y equals the absolute value of x minus 3. This is y equals 1/4 the absolute value of x minus 3. And that gives us the curve that it's going to be based on, again, the transitions and the transformations that we can work with. There are, again, multiple different examples of these based on the original functions we're playing with, but this here is the list of all possible different transformations we can have.